All right, we are in section 2.2. We're learning about graphing our other four trig functions. So let's start with y equals tangent x. So again, this is where we plug in values for x, which are the angle. So our domain is the angle. And then we get out values for the ratio. So range, or the y value, is the ratio associated with that angle for that trig function. So going to the chart we've been memorizing, remember, we can find tangent just by going sine divided by cosine. So for 0, it would be 0 divided by 1, which is 0. So we'll have a point at 0, 0. What is the tangent of pi over 6? So this will be 0, and then I think the tangent of pi over 6 is, I always forget which one's which, but so it's 1/2 over square root of 3 over 2. So it would be 1 over square root of 3. So that, as a decimal, is 1 divided by square root of 3 is going to be 0.57. This is very approximate. We'll just call it like 0.6. Pi fourths tangent is sine divided by cosine would be square root of 2 over 2 divided by square root of 2 over 2, so that's 1. And then pi thirds is square root of 3, and the square root of 3 is 1.7. And then pi halves would be sine is 1, cosine is 0. So when we try to do 1 divided by 0, we can't do that, so we call that undefined. So something I already have here on my graph that I didn't erase from what I wrote on here last year. I've already got my asymptotes placed at pi halves and 3 pi halves, because in those two, for those two angles, tangent is undefined, because when we try to do opposite over adjacent, we're dividing by 0 and we can't do that. So I've already got those asymptotes marked in there. Okay, so let's start sketching what we've got. So we've got a point at 0, 0, and we have a point at pi 6, 0.6, so a little bit here lower than 1. Notice I scaled this graph differently than I did in the last notes. And then pi fourths would be here in between at 1. And then pi thirds would be up at 1.7. Now, we may want some other points in here to kind of really see what's happening. So if you want to, just pick some other angles that are close to pi halves. So remember, pi halves is 90 degrees, and pi thirds was 60 degrees. So let's just find some random values. If we want to go halfway in between, we could do 75 degrees. And seriously, just use a calculator, because we're just discovering what this is going to look like. So tangent of 75 degrees, make sure I'm in degree mode. I am. My calculator says that that is 3.7. So that would be almost up here at 4. So you can see our tangent starts to increase, kind of like a parabola or like an exponential or something here. And of course, we know there's an asymptote where it's undefined, so it's just going to get closer and closer to that asymptote but never cross it. So if you plugged in bigger numbers like 80 degrees or 89 degrees, you're going to get larger values for tangent. Here, just for fun, I'm going to do tangent of 89, and it's 57. So see, our numbers just keep getting bigger, but they never quite get to the asymptote. Okay, so let's go on to quadrant 2, where we have 2 pi thirds. So that's going to be the same value as pi thirds, except remembering our little quadrants mnemonic device for remembering what's positive where. So we have quadrant 2, only sign is positive, so tangent is going to be negative. So even though pi thirds and 2 pi thirds have the same value, it's going to be a negative value. So negative square root of 3, or negative 1.7. And then pi fourths would be a negative 1, 3 pi fourths, 5 pi 6 is going to be negative 0.6. And then pi back down to pi is going to be back to 0, right? Then the next couple values are in, well, the next one value, I guess, is in quadrant 3, in quadrant 3, tangent is positive. It's going to be the same ratio as 3 pi fourths and pi fourths, which is a 1 or a negative 1, but it's positive in quadrant 3 because sine and cosine are both negative. So negative divided by negative is a positive 1. And then over in quadrant 4, we have cosine is positive, but sine is negative, so when we divide those, we get a negative value again. So just kind of throwing in some key points here as we start to discover what this graph actually looks like. Back to 2 pi is obviously going to be the same as 0. 9 pi fourths is the same as pi fourths. All right, sketching in the rest of those values then, we have at 2 pi thirds, we have negative 1.7. So 2 pi thirds right here. Negative 1.7 would be about here. And then 3 pi fourths is in between. That'll be at about negative 1. And then 5 pi 6 will be at about 0.6. Pi is at 0. 7 pi 6, oh, we didn't do that one. So 5 pi fourths is in between here at 1. And then we have undefined here. We already have our asymptote in there. And then 7 pi fourths is in between 5 pi thirds and 11 pi 6. So that's going to be at negative 1. And then at 2 pi, we're back up to 0. So hopefully you can see how this, my sketches are terrible. Kind of see how this is going to repeat over and over. Here, I think I drew this out a little bit better last year. So let's look at last year's sketch instead, so I don't have to go through all the effort. Oh, look, I even have a chart of a bunch of bigger angles that I found the values for to show how that tangent value gets bigger and bigger for larger angle values closer and closer to 90. We can't do 90 itself, but we could do like 89.5, 89.9, and it's just going to keep getting bigger. 89.9 is 572. So you can see it's approaching infinity the closer we get to 90. Okay, so something that's really interesting about tangent is instead of it repeating every 2 pi, I don't know if you noticed this, but it actually repeats every pi. And it's kind of like an x cubed graph, just restricted by these asymptotes. So we have these branches of the graph every pi repetition instead of every 2 pi. You know, that kind of has to do with the fact that in our all students take calculus thing, these two quadrants are where tangent is positive and these two are where tangent is negative. So it just keeps alternating between those values. And that changes every pi, rather than every half a circle around, rather than just every full circle. Okay, so since the period is pi, the domain, so the period is pi, but the domain, instead of being all real numbers, we have these asymptotes that interrupt our domain at values of pi halves. So pi halves, 3 pi halves, 5 pi halves, 7 pi halves. So the way that we would indicate that, one way of indicating that domain is by saying what x can't be instead of what x can be. So this is our set notation with saying x can be anything except for pi halves plus any values of k pi, because if we add pi to that, we'd have 3 pi halves, add pi again, we'd have 5 pi halves, subtract pi, we would have negative pi halves, and that's always where our asymptotes are going to hit. Now the range on tangent is all real numbers, because these values approach negative infinity as they approach the asymptotes, and positive infinity as they approach the asymptotes the other direction, right? So y values, the ratios we get out of tangent can be anything. They're not restricted to between 1 and negative 1 like sine and cosine are. Obviously we can see our asymptotes are where the domain does not exist. So here's two of the asymptotes. The first two that would be considered our, our key points to use in graphing. Other asymptotes could be distinguished infinitely. Whoops, I didn't mean to write a 3. By just doing what we did up here for the domain, just calling it like pi halves plus k pi. And that will give us infinitely many asymptotes. And of course, an asymptote is a line. It's not just a point. It actually needs to be distinguished by an equation. So we have an asymptote x equals pi halves, x equals 3 pi halves, x equals whatever pi halves plus another value of pi. So those are our asymptotes, vertical asymptotes. And then our x-intercepts happen at every interval of pi itself. We've got one at 0, one at pi, one at 2 pi, there'll be one at 3 pi, 4 pi, negative pi. So we can just say our x-intercepts happen at values of k pi comma 0, right? Those are our main ones right there. Okay, so this is our basic parent graph for tangents.